Welcome back to the deep dive. Today, we are tackling a paradox that I think has been bothering a lot of us lately, even if we can't quite put our finger on it.
Hmm.
We have these massive AI models, right? Trillions of parameters, huge data centers. And sure, they can write a Shakespearean sonnet about a toaster in like 5 seconds.
It'll be a pretty good sonnet.
It'll be a great sonnet. But then you ask them to do something that needs real, structured logic like diagnosing a specific knee injury from a 3D scan or solving a really nasty Sudoku puzzle, and they just fall apart.
It's what they call the illusion of fluency. The language is so perfect that we assume the reasoning behind it must be just as solid.
Right.
But when you actually test for that raw, multi-step logic, you see the cracks almost immediately.
Exactly. So today, we are looking at the next evolution of AI reasoning. And the premise here isn't about making the models bigger, it's about making them smarter.
A different approach entirely.
We've got two fascinating papers on the table. The first is 3D reasoning, which comes from researchers at Harvard Medical School and a few other places.
And the other is the hierarchical reasoning model, or HRM, from Sapient Intelligence and Tsinghua University.
And what I love about pairing these two is they're attacking the exact same problem, but from completely opposite ends of the spectrum.
They really are. The medical paper, 3D Reason-E, basically argues that the model itself is fine, but it's blind.
Blind.
Yeah, it can't reason because it isn't grounded. It doesn't know where to look or how to think like a doctor.
Okay, so it needs better data, better instructions.
Exactly. But the HRM paper says no, the problem is the architecture. It's the AI's brain that's wrong. And if we want it to reason like a human, we need to build it more like a biological brain.
So we've got medical boot camp on one side
Uh-huh.
and a total brain transplant on the other.
That is a very good way to put it, yes.
All right, let's start with the boot camp, 3D reasoning. So playing devil's advocate, we have incredible vision language models now. Why can't I just upload my MRI and get a diagnosis? Why is this still so hard for AI?
You would think it's just image recognition, wouldn't you? But there's a huge difference between looking at a 2D picture and interpreting a 3D volume.
Okay.
Current VLMs are great at, global tasks. You show it a photo of a park, it says, that's a park with a dog.
Sure, easy enough.
But medicine needs what the paper calls fine-grained 3D grounded reasoning. An MRI isn't a picture. It's a volume of pixels, voxels. And the actual problem, the tear or the lesion, might be a tiny cluster of voxels buried deep inside that 3D space.
So the AI can see the whole knee, but it can't find the specific little tear in the meniscus because it doesn't know how to navigate that 3D space.
Exactly. It hallucinates. It might just guess meniscus tear because that's a common injury it saw in its training data.
Yeah.
Not because it actually found the tear in your specific scan.
I see.
The paper points out that clinicians use a very specific process, something called a region-first workflow.
Okay, so unpack that. What's the doctor doing that the AI isn't?
A radiologist doesn't just glance at the whole knee and guess. They zoom in. They identify a very specific subregion like the lateral central tibia.
Right.
They mentally isolate that tiny box. Then and only then do they look for problems. And finally, they assign a severity grade using a strict framework. In this case, it's called MOA case. MRI osteoarthritis knee score. It's a standardized system. The problem is general AI models have no idea where the lateral central tibia is in a 3D scan, and they certainly don't know the MOA case rules.
So it's a funnel. Locate, assess, grade, and the AI is trying to jump straight to the end.
Precisely. And that's why these researchers built 3D Reason Knee. It's an attempt to force the AI to learn that funnel. We're talking nearly 8,000 3D knee MRI volumes.
But the thing that really caught my eye was the data structure. They call them quintuples.
This is the secret sauce. This is the whole thing.
Right.
Most AI training is just image and label. This is a cat.
Right.
But for this, they provide 5 distinct things to the model for every single data point.
Okay, walk us through the 5.
1, the 3D MRI itself. 2, the diagnostic question. 3, and this is the critical part, a 3D bounding box.
So they literally draw a box around the problem area.
They highlight the exact voxels the AI needs to look at. That is the grounding.
Got it.
4th is a chain of thought, the actual step-by-step sentences a doctor would think to themselves. And 5th, the final MOA case S grade.
So they're not just testing if the AI gets the answer right. They're literally giving it the map, the compass, the instructions, and the destination.
They are trying to bridge that gap between just recognizing pixels and actual clinical reasoning.
Yeah.
And the effort here, it was immense. Over 450 hours of expert clinician time.
Wow.
We're talking board-certified radiologists and surgeons sitting there drawing boxes on MRIs and writing out their thoughts.
It's a serious labor of love. So they build this gold standard data set, And then they test the big AI models against it. How did they do?
Not well. Not at all. They tested models like Quinn 2.5 VL, even O1 from OpenAI, in a zero-shot setting, so just showing the MRI and asking the question.
With no help.
Right. With no help. Yeah. The accuracy was abysmal. Quinn 2.5 got around 15.8% accuracy.
15%. That's basically random guessing.
It really is, and it highlights what they call the localization bottleneck. The models failed because they just couldn't find the right spot. If you're looking at the femur when the tear is in the tibia, your reasoning is doomed from the start.
But surely, with all that extra quintuple data, they could teach it to do better.
They did. When they provided the instruction schema, basically the rulebook for MOA case, it helped a little. But the real jump, the big improvement, happened when they gave the AI the ground truth region.
They showed it the box.
They literally cropped the image to just the relevant part. When they did that, accuracy shot up. The O1 model improved by almost 20%.
So if you hold its hand, tell it exactly where to look and what rules to follow, it can start to do the job.
It can do a better job, yeah. But the big takeaway here is that these generalist models, they aren't naturally good at this kind of 3D spatial reasoning. They need that explicit, expert-level hand-holding.
Okay, which brings us perfectly to the second paper. Because if the medical researchers are saying we need to spoon-feed the AI better, the folks behind the hierarchical reasoning model are saying, well, maybe the AI's brain is just wired all wrong.
It's a fantastic pivot. The HRM paper argues that the standard architecture for almost all modern AI, the transformer, is, and I'm quoting here, paradoxically shallow.
Shallow, but we're always hearing about deep learning.
We are, but think about how a large language model actually works. It just generates one token at a time. To get it to reason, we use chain of thought, where we prompt it to think step by step.
Right, asking it to show its work.
But that work is just more text. It's a straight line. The HRM researchers argue this is slow, it's brittle, and it needs a ton of data. If the model makes one mistake at token 5, token 50 is going to be completely off.
There's no backspace.
No backspace.
Yeah.
No pausing to reconsider.
Yeah.
So they looked at biology, at the human brain, and said, that's not how we think.
So how does the brain do it, and how does this HRM model copy it?
The brain uses two key principles: hierarchical processing and temporal separation. You can think of it like a company with a manager and a worker.
Okay, I can picture that.
In the HRM architecture, they built two distinct recurrent modules. There's the high-level module, let's call it the H module, the manager, and the low-level module, the L module, or the worker.
And what's the division of labor there?
This is the cool part. The manager, the H module, operates slowly. It does abstract, big-picture planning.
Yeah.
The worker, the L module, operates really quickly, doing all the detailed, low-level computation.
So how did they communicate without getting in each other's way?
Through a mechanism they call hierarchical convergence. The manager sets a plan, a general state. Then it basically goes to sleep.
Okay.
And the worker takes that plan and just iterates like crazy, running calculations over and over until it solves that specific part of the problem and reaches a kind of equilibrium.
A local equilibrium. So the worker just churns away on its one little task.
Exactly. And only when the worker is done does the manager wake up, check the result, update the overall plan, and then it resets the worker for the next step.
That sounds incredibly efficient. So instead of one massive network trying to think in a straight line, you have this rhythm. Plan, execute, check. Plan, execute, check.
And the efficiency stats are they're staggering.
Yeah.
The HRM model they built has only 27 million parameters.
27 million. GPT-4 is supposedly in the trillions. Even the small models we run locally are, 7 or 8 billion? 27 million is nothing.
It's a rounding error. And it was trained on only 1,000 examples.
Okay, but can a model that small actually do anything useful?
Well, this is where it gets wild. They didn't test it on poetry. They tested on things that consistently break standard LLMs, specifically Sudoku Extreme and Maze Hard.
Sudoku Extreme sounds painful. Why is that so hard for AI? It's just a logic puzzle.
Because it requires deep backtracking. You put a 5 out in a box. 10 moves later, you realize that 5 makes the whole puzzle unsolvable. You have to go all the way back, erase it, and try a 4.
Ah, and the linear chain of thought models can't go back.
They really struggle with it. The standard models got 0% accuracy on these tasks. 0. HRM got near perfect scores.
That is a beatdown, a complete shutout.
And it gets better. They tested it on the ARC AGI benchmark.
ARC, that's the abstraction and reasoning corpus. That's considered the IQ test for AI, right?
It is. It's one of the hardest tests for general intelligence because you have to figure out brand new rules for just a few visual examples. You can't just memorize the answer.
So how did it do?
HRM, with its tiny 27 million parameters, scored
Is
40.3%.
that good? I know the scores on ARC are usually really low.
To give you some context, Claude 3.7, a massive, state-of-the-art model, scored 21.2%, and O3 Mini High got 34.5%.
So this tiny brain-inspired model beat the absolute heavyweights on a pure reasoning test.
By a huge margin. And it did it all internally with that manager worker loop, not by generating thousands of words of text.
They mention another feature, ACT, adaptive computational time. What is that?
It's basically the thinking fast and slow idea put into code. The model has a little internal decision maker, a Q-learning head, that asks itself, am I done thinking about this step?
So it can decide how much effort to put in.
Exactly. If the problem is easy, like 2 plus 2, it halts early. If it's a really complex maze, it lets the manager and worker run for more cycles.
That's so human. You ask me a simple question, I answer. You ask me a riddle, I stare at the wall for a minute.
Right. And because of that, it saves a massive amount of compute. It focuses its energy only where it's needed.
Okay, the performance is incredible. But there was this one part of the HRM paper that just blew my mind. It felt less like computer science and more like biology. The section on neural dimensionality.
Ah, yes. This is the aha moment. This is where it all comes full circle back to neuroscience.
So break this down for us. What did they find inside this AI's brain?
Neuroscientists have a metric called the participation ratio, or PR. Basically, it's a measure of how complex or high-dimensional the neural activity is in a certain part of the brain.
High dimensional, meaning a lot is happening at once.
Sort of. Imagine a party. If everyone is chanting the same thing, that's low dimensionality. Simple, focused. If everyone is having their own complex, overlapping conversations, that's high dimensionality.
Got it.
Well, in a biological mouse brain, the sensory areas, the parts just processing raw input, have low dimensionality. But the association areas, the part doing the planning and thinking, have very high dimensionality.
So simple input leads to complex thought.
Exactly. Now, the HRM researchers did not program this into their model. They just set up the manager and worker and hit train. But when they analyzed the trained model, they found the exact same pattern had emerged on its own.
You're kidding.
The low-level worker module stayed low-dimensional. The high-level manager module had developed extremely high-dimensional representations.
So it naturally organized itself like a biological brain.
It did. And here's the kicker. They checked an untrained model, one with random weights, and the structure wasn't there. This hierarchy wasn't hard-coded. It was a learned trait of intelligence.
That is just wild. We build a mathematical model to solve Sudoku puzzles, and it accidentally reinvents the structural organization of the cortex.
It really suggests that this separation, low-dimensional execution, and high-dimensional planning might be some kind of fundamental law of intelligence, whether it's in a mouse, a human, or a piece of code.
So let's try and put these two deep dives together. What's the big picture? On one hand, you have 3D reasoning telling us that for AI to work in the real world, like in medicine, it needs to be grounded.
Right. It has to know where to look and what steps to follow. Data and structure matter.
But on the other hand, HRM shows us that just scaling up our current models might be the wrong path for true reasoning. We might need a whole new kind of architecture, something more recursive, more, well, brain-like.
It feels like a clear shift toward what people are calling System 2 AI.
System 2.
Yeah, from psychology. System 1 is that fast, instinctive gut reaction. Most current LLMs are System 1. They just reflexively predict the next word. System 2 is slow, deliberate, logical planning. Both of these papers, in their own way, are trying to build that System 2 capability into AI.
It really feels like we're at a turning point. For the last few years, the answer to every problem in AI was just make it bigger, more data, more GPUs. But HRM just beat the pants off supercomputers with a tiny, specialized structure. It raises a huge question for the whole industry. Are we at the end of the bigger is better era?
If a 27 million parameter model can out-reason a billion parameter model just by being organized differently, then yeah, maybe efficiency and architecture are the new frontier.
And you have to wonder, if we're building machines that naturally develop the same neural structures as our own brains, does that bring us a step closer to understanding our own consciousness? Or are we just building a really, really good Sudoku player?
That is the ultimate question, isn't it? If the math and the biology lead to the same solution, maybe we aren't so different after all.
Something to think about. Thanks for listening to The Deep Dive. We'll catch you next time.